We are talking about ionic charges and how to write ionic compounds, the formula of ionic compounds. So let's call it ionic charges. So compounds, as you know, they're made of more than one element that are chemically bonded. So there is a chemical bond between those elements. It could be depending on the type of element, ionic, covalent, or if it's just a metal, would be metallic. But sometimes we have all of these bonds all together. I'll give you an example. Sodium carbonate. Well, we have many different elements. We have sodium, which is a metal, but then we have a carbon and oxygen that is a non-metal. However, overall, this is an ionic bond. Ionic because it's made by the electrostatic interaction of oppositely charged ions. And in this case, the opposite ions are the metal and the carbonate. So this that it's made by two non-metals, so we have a covalent bond between those elements. However, because there is an excess of charge, it will form an ionic bond. So the tricky thing about writing this ionic compound is that some what are called the polyatomic ions, we need to know them. Polyatomic ions. And those are the most common: hydroxide, carbonate.
Yeah, I've remembered two of them.
Sulfate. Because not only polyatomic ions are important, another one could be phosphate, but there are some metals that we just need to know the charge of. But polyatomic, just think about what it means. Like, I wrote it really horribly, so I can maybe rewrite it. So it's polyatomic ions because are made of more than one element. Polyatomic, more than one element, but still overall it's an ion. So this is really wrong. It's minus. Okay, so hydroxide, carbonate, sulfate, phosphate. We have some positive ones too. Ammonium.
Phosphate was in the test.
Which one?
Phosphate or whatever.
Phosphate, exactly. So as you can see, also the more time you see, you hear them, you write them, then you will be like, oh, I've heard that before, until you'll be like, yeah, I know them exactly by heart. Okay, and we need to practice of how to write these compounds using those charges that, as we can see, they are sometimes it's not very easy because we needed to balance these charges between a metal and a non-metal. But there are also some metals that we would need to know the charges of, because metals that some we know them because we can find them from the periodic table, like group 1, group 2 metals. They are always going to have the same charge, so +1 and +2, depending on the groups. But there are some others, like transition metals, that they can have variable charges, so we should be familiar with the most common ones. And maybe you've come across zinc, copper 2+, zinc is also 2+, silver is just 1+, iron can be 2+, as well as 3+. Okay, but there is one thing. Sometimes, let's say, for example, iron oxide. Because iron can exist in two different oxidation numbers, we needed to know which one is present in this compound, iron oxide. That's why sometimes we would see this name as iron with, or whatever metal, with a Roman number in the bracket. And this tells us the charge of that metal. So we would have two different options like this: iron 2 oxide and iron 3 oxide. Okay, so polyatomic ions, metals, and now we need to learn how to bring them together, because compounds are neutral. So we need to make sure that all of the charges are balanced. Let's do an example. We could have a very easy ones. Let's say that we have magnesium oxide.
Yeah.
Okay, this one, well, first thing, we should look at the periodic table to work out the charge. We know that magnesium is 2 plus according to the periodic table. Oxygen is 2 minus. As we can see, they have the same charges, so we will need just one of each in order for the compound to be neutral. So in this case, it's a bit easier, but we could have a bit more difficult ones, like aluminium. Aluminium oxide. In this case, aluminium 3 plus, oxygen 2 minus, but the charges don't balance out completely and straight away. So what we could do, we could use this drop and cross method, where the charge of one of the atom becomes the number of the other one. So we would write this as aluminium, little 2, oxide, little 3. Essentially, we've made aluminium become a 6 plus and oxygen become a 6 minus overall, so that overall they balance out. And this drop and cross, it's useful for the polyatomic ions because we would need it to balance these charges. What is important to remember is that if we are multiplying all of the ions, we need to put them in bracket. An example, let's do sodium sulfate. Sulfate, sodium, it's +1, sulfate, we have it right here. In this case, is the sodium that we have to multiply by 2, always with the little number next to it, because we need the 2 of them to neutralize that charge. Okay, remember, if we are multiplying the polyatomic ion, we need to put them in bracket with the little number there. So we will look at some more examples now. If you really want to learn this, because I know it's like a list, so it's a bit difficult. So unless you find some mnemonics or some kind of, maybe visual aid, what it's useful for this is write all of the ions in a post-it or on a little revision card. And when you have to do the practice, rely on this. Yeah, just practice it by looking at this revision card until with the time, so with the continuous the continuous practice, you will realize that you don't need to look at this anymore, just because you've been exposed to it so many times that then you just know it. Okay, but to start with, I think it's useful to have that visual help. Yeah, of list of atoms. Okay, I need to write the name. I will just look at my list and work it out until you look less and less and less. And this will mean that you've just naturally learned it. So now let's do some examples. First step, periodic table. And we can work out, because we need to see if if we can work out the charge from the group number. Magnesium is in group 2, fluorine is in group 7. What does that tell us about their charges? So taking a step back, we are talking about understanding the charge of elements by looking at the periodic table. Let me just clear it up a little bit to help focusing on not so many colors, because it's a bit too confusing. Okay, and me out of the way. Okay. So the group number tells us the number of electrons in the outer shell. Okay, so number of electrons in the outer shell of atoms. And knowing that, we can work out how many electrons are needed to be gained, lost, or shared for elements to have a full electronic configuration. And the full electronic configuration would be for this one, because those are the noble gases and they have a full outer shell. And all elements, they want to have the same number of electrons in the outer shell as the noble gases, because in this way, they are stable, because they have a full outer shell. We can write the group numbers in different ways, like 1 to 18, but we will focus, and in your periodic table in the book, I'm sure that you will have them as like this. Sometimes group 8 is also group 0, because they just have a full outer shell. So what we need to think about is, okay, the element is in a specific group, and let's take magnesium as an example, is in group 2. What does that tell us? Well, it tells us that it has 2 electrons in the outer shell. Okay, how do we work out how it reacts? Well, we need to think about how does it get to the same number of electrons as a group 8 in the easiest way possible. So if we look at the total number of electrons of magnesium, we have 12, right? In total, because the atomic number tells us the total, of course, even though it's only the outer shell ones that react. But in total, because this is a way to find it out, which I think it's quite easy looking at the number. Magnesium has 12 electrons in total. So it needs to get to the same number of electrons as noble gases. So the two options are, and we always need to look at the closest ones. Well, the one right before it, it's neon with 10, and the right after, it's 18 argon. We cannot jump too many steps, too many periods, ahead, but just the adjacent ones.
Are you jumping between groups or period? Like,
we're just considering as number of electrons. So we don't focus too much on whatever whatever all these boxes in the periodic table mean, but just what it tells us about the number of electrons. Because what this tells us is that magnesium could, to have a full outer shell, it can gain 6 electrons, and in that case, it would have 18. Or it could lose 2 electrons, and it would have 10. And we know that that's a stable number because it's the same number of electrons as noble gases. But what's easier, 12 to 18 or 12 to 10? Always the shortest way, and it would be 12 to 10. So this tells us that if magnesium loses its 2 outer electrons, so it would go from an electronic configuration of 2, 8, 2, because it has 2 electrons in the first shell, 8 in the second one, and 2 in the third shell, for a total of 12 electrons. If it loses 2 of them, it would become 2, 8. It would get a 2 plus charge, and it would have a total of 10 electrons. And that's a stable. We know it's a full electronic configuration because it's the same as neon. And we know those noble gases, they have a full electronic configuration. Let's look also on the opposite side. Let's look at sulfur as an example. Sulfur is in group 6. What it tells us is that it has 6 electrons in the outer shell. Okay, so we know that we can look at it in this way, like, well, if it has 6 electrons, it needs to get to 8 electrons in total. So how does it do that? Lose all of them and have the previous shell full, or gain some? Well, in this case, 2. It would just gain 2, because, and that's why we can see in both ways as how does it get to 8, or what's the closest noble gas, and we want to get the same number of electrons. So sulfur has an electronic configuration of 2, 8, and 6, with a total of 16 electrons. The closest number of a stable configuration is argon with 18, so that's where it would want to get. It would form a 2, 8, and 8 electronic configuration, 18 electrons in total. So we know that the charge that sulfur is most likely to have, it would be a 2 minus. So that's how we can use the periodic table to work out charges of elements. Okay, and like this we can apply to writing full compounds. So for sodium, for example, group 1 become +1. So think about it in terms of atomic number, or just if it's in group 1, the easiest way we know it's get rid of that outer electron, so become +1. It's important that you find your own way that it's just logic for you. Also because fluorine, for example, 9, we need to get to 10, or group 7, it needs to have 8 electrons in the outer shell. So it would become F with 1 extra electron. We really need to stop and think about it one moment more, as gaining electrons means becoming negative, because it's gaining negative charge. So it's really, really important to take just a few seconds longer to analyze that. Okay.
Yeah. Okay, so the next one, it would be I just can't. Oh, it would be -3.
Well done. Well done. Normally we write it as like this, 3 minus, perfect.
And then would the next one be +2 or +1? No, +1.
Beryllium, it's over here. Which group is that?
2.
Yes, therefore.
+2.
Exactly. Next one.
That would be -3.
Sorry, if you said sorry, I didn't hear. I was closing the window.
-3.
Perfect. You're getting it.
That's just made it a lot easier.
It's good. I'm happy. It's really important. After having done all of these examples, we could also notice that, well, all the elements in group 1, they will have the same charge. Because if elements have the same electrons in the outer shell, well, they have the same charge. In fact, group 1, it's +1. Group 2, it's +2. Group 3, +3. This, they could be -4, but they prefer to share electrons because it's right in the middle. While then we go to -3, -2, -1. Okay,
Yeah.
so maybe you're more confident in remembering this. Group 1 elements become +1, or you prefer working out the charges by looking at the atomic number, or maybe you prefer to think about how to get to a full shell, which is 8, which could mean gaining a full outer shell or removing some electrons to make the previous one full. Whatever way it's easier for you to find, it's a really fundamental concept of chemistry. So one important thing to notice is that ide means this atom it's a negative ion form. So in fact, the fluorine is the element, fluoride is the ion, which means that oxide tells us it's the oxygen in its negative ion form. Let's go over the key tips on how to find the formula of ionic compound, so to work out charges and to write a full compound. If it has the ide, it means that it's an element in its negative ion form. How do we know the charge? We look at the periodic table. And by looking at the periodic table, at the group number, we can work out how many electrons do they need to gain or lose to get a full outer shell. If you have 8, yeah, maybe it's a polyatomic ion, because most of the polyatomic ion, carbonate, sulfate, phosphate, nitrate, those that have more than 2 oxygen, normally they have an 8 at the end. Okay, the only different one is hydroxide. That's hydro, hydrogen, oxide, oxygen. So something to be familiar with. And to work out the overall charge, the easiest way probably it's always this drop and the cross. The charge of one number becomes the little number next to the other element, because in this way we can balance the charges. And if we have a polyatomic ion, we need to make sure we put it in the bracket, because we timed the whole thing by whatever number we need to make it neutral. I think those are the key tips. So I think this is a really nice revision card to have, either a post-it or a little square revision card, write it inside your book, but I think those are the main ones to know. Remembering that most of them, like the non-metals and some more common metals, we work them out from the periodic table, but having a list that you can have easy access, it's really important. Make it tidy, make it pretty, and always refer to it until you won't need it anymore because you've learned it.